So thank you. Yeah, thanks for coming. Thanks for those of you who came along to the open house as well. We're doing this kind of stuff, this CHATS seminar series, so that you can learn a little bit about exactly what kind of research do the faculty do when they're not teaching you in class. We have to have something else to keep us busy for the remaining hours of the week, right? And one of those things is research. And so what I want to try and do over the next, I think it'll take about 30-35 minutes, is give you a little bit of a snippet of the kind of research that we do in my group, just one of the projects that we have going on. And hopefully it'll give you some idea of how it is that we spend taxpayer dollars, your money basically, right? The first thing I have on this slide of any importance, other than the title, is the people who paid for the work. Research is kind of expensive, and hopefully by the end of 35 minutes, you're not disgusted, you don't go home to your parents and complain about waste of taxpayers' money by the Department of Energy and the National Science Foundation, okay? So I'm going to talk about complex oxide materials. If you don't know what a complex oxide is, no problem. Minerals to next generation electronics. I'm going to tell you about some very old materials that we're trying to do some things in the future that I think are pretty exciting, okay? So here's the outline. There are, 2 or 3 faculty here. I'm not going to talk to them. I'm going to completely talk to everybody else. 75% of my talk is introduction, okay? And then at the end, I will show you basically 10 minutes of a research detail. I can see I'm being timed back here for accuracy. Okay, so I'll talk about oxides, a very gentle introduction to what oxides are, why they're important. I'll tell you about complex oxides, what that word means, and then I'll tell you about this family of materials called perovskites, that there are, literally hundreds of research groups around the world who are really interested in perovskite oxides. I'll try and explain why, okay? And then talk about what I find very compelling about them, the fact that we might be able to solve some of the world's problems using these materials in oxide electronics, and then one very quick example. And it's an example, if you're a math sci student, you've probably seen before, you probably got the idea already that defects aren't always bad. I will show you here an example where defects do something that's actually pretty good for you, okay? So just to start at the very beginning, everything I will talk about today will be an oxide, and therefore this stuff is pretty important. Pretty important to us, obviously. For similar reasons that it's important to us, it bonds with almost everything in the periodic table, right? You can make a lot of oxides, and that is something that I will hammer home in the first part of my talk. So basically everything out here, transition metals, left side of the periodic table, even the metalloids, they like to bond with oxygen, and often they make solid materials that we call oxides, right? So what do oxides do for the world? Here's a few examples, right? Very versatile, very useful materials. If you're taking ceramics right now, you know this, right? And you're getting to learn more and more that oxides are really useful ceramic compounds. So alumina is a classic example, just aluminum oxide, it's an electrical insulator. We use it all the time for various properties. Silicon dioxide, an incredibly important material historically that I'm going to return to later on. This is what happens if you take a wafer of silicon and you oxidize the top surface, you make silicon dioxide. And the way you do that is a beautiful defect-free process that fueled microelectronics for decades, okay? At some point that ran out of steam, and the reason it ran out of steam was because the dielectric constant of SiO2 is not as big as it could be. And so there was a flip, there was a massive sea change in that industry from SiO2 to hafnium dioxide. You could ask yourself, how complicated could that really be to go from silicon oxide to zirconium or hafnium oxide? It cost easily more than $1 billion of research and development money to make that flip. And I will return to that later on. And that will be one of my motivations for maybe there's a way to do this that's a bit better than that, okay? And then another one, a random example, chromium trioxide is one of my favorites, right? So, you guys can work this out. Oxygen's in group 6. It's a chalcogen. It likes to be 2-. So this is 6 negative charges. Chromium trioxide, very useful material. It's hexavalent chromium, chromium 6+. And right here, you've seen the movie. It does all sorts of interesting things, but also some bad stuff. What's the movie I'm talking about? Only the old people in the room know the answer to this, right? Erin Brockovich, which is a fantastic movie if you've not seen it. Go. Yeah, it's no offense. You are bigger than me too, okay? Erin Brockovich, if you've not seen it, go and watch this movie, it's really good. It's about a power company that uses chromium trioxide in solution to prevent rust from forming, right? That's one of the great things that chrome does, right? Chromium. And unfortunately, they let it leach into the groundwater, and a lot of people got very sick as a consequence. It's a really interesting film, okay? So applications, what do you use these things for? they're just everywhere, right? Ceramic oxides are all over the place, used for a million different things, right? So some ones I'd really emphasize: mechanical resistance, used all the time for mechanical properties. They can be glasses when they're amorphous, dielectrics, catalysis, very common materials used in catalysis. This material, right, one of the most important materials right now that you can imagine. Lithium-ion batteries are essentially enabled by this material. And then this one, which is a very interesting geopolitical situation with indium at the moment. But indium tin oxide was, and it, to some extent still is, the material that's used in laptop displays and touchscreen displays and phone displays. And for various reasons, we're running out of indium, basically. There's not a lot of it to begin with, and other oxides are now being explored, right? So just a brief aside, transition metal oxides are special. They're special because they can be magnetic. I love magnetism, so I care about that. It'll come up later in the talk. And they can also conduct electricity very well. So we'll see that transition metals are actually really important types of oxides, okay? So this, even though there's a lot of it, is the tip of the iceberg for oxides. And the reason I say that is because there are also complex oxides. So everything on this page, I have just one element with oxygens, what's called a binary. Right? But there are also complex oxides where you have more than one element bonded with the oxygen. And it turns out that this really opens a huge box of possibilities, right? This is by no means an exhaustive list, right? I could just keep going and writing family after family after family of complex oxide materials. They're written with complicated formulas. This means element A, element B, 2O4. This is an example. There's a crystal structure called a spinel. There are garnets, hexaferites, pyrochlores. There are even series that have in them, in principle, an infinite number of compounds, even though only 3 or 4 of them have ever been made, okay? I want to make 2 more points about this. One is that they're basically gemstones. They're precious or semi-precious stones in many cases. They look beautiful. In fact, a lot of the world's most famous, most storied rubies are actually nothing other than spinels. X-ray diffraction was used to show that, to everybody's shock and horror who was involved in that industry, because they think of spinels as being really not worth all that much. And these were rubies that were worth, many millions of dollars. So naturally occurring minerals in many cases. The first discovery of these compounds was made in the form of a mineral. And of course, I'm not going to go through all these families. I'm going to talk about only one that I find particularly fascinating, called perovskite oxides, okay? And every perovskite oxide has the chemical formula AbO3, right? So it looks super simple, and I'll show you that there's a bit more to it than you might imagine. So some history on perovskites. So like I said, it's a family. The mineral prototype, the first one that was discovered, literally dug out of the ground, looks like this, was calcium titanium O3. It was not actually discovered by Perovsky. The name comes from this person, Lev Alexeyevich von Perovsky. Actually, it was named in his honor. He was president of the Russian Mineralogical Society at the time when this was discovered by 2 unknown people, basically. They named it in his honor, which is pretty incredible. And that's why they're called perovskites, right? So what happened from 1840 to 1920 can be pretty much summed up as almost nothing. Very little was done with perovskites, right? Goldschmidt did a little bit. He made some fantastic guesses. He guessed that it was actually composed of calcium, titanium, and oxygen, and that the ratio really was 1:1:3. And it was not until 1945, so if you've taken Maths I-3011, that's way after when the Braggs developed X-ray diffraction. It wasn't until 1945 that somebody even bothered to check that the crystal structure was what Goldschmidt guessed it to be, and they found that in fact it was, okay? So this is, a really important point. If you haven't grasped this yet, if you learn more about science and read more about science, you will grasp it. Science is a human thing, and it does not go in a nice logical progression. It goes all over the place with many mishaps. People ignore things for decades, and this is a classic example. Basically, nothing happened. 1945, this structure is known. 40s and the 50s, a few chemists play around making a synthetic version of calcium titanate. But nobody just said, well, if I can put titanium there, probably I can put a whole bunch of this stuff in the middle of the periodic table, so let's do that in a systematic way. If they did that, they would definitely have won 1 Nobel Prize, and you can make an argument that maybe they would have won 2 Nobel Prizes, right? But that's not what happened, and they basically lay dormant, and then something happened in the 80s which got people interested, okay? So this is the crystal structure. This is a deja vu if you're in ceramics. We just went over this the other day. This is what the unit cell looks like. So AbO3, A is the green stuff, goes on the corner. The cube's about 4 angstrom. B sits in the middle, and it's surrounded by oxygen in this octahedral cage. And the oxygen connects itself by corner-sharing octahedra, which would make Linus Pauling happy. If you're in my class, you know what I mean by that, right? So this is the basic unit cell, okay? So why do I like perovskites so much? Why do people like perovskites so much? Well, here's one thing about them that's pretty impressive, right? So even if I just pick oxygen, and there's a whole bunch of other stuff that makes perovskites, right? If you've read about recent things in the solar cell world, you know that you can also make organic, inorganic, hybrid perovskites, and they're extremely hot and very promising. But ignoring those, just take oxygen. If I paint green in the periodic table, what I can put on the A site in a perovskite, and I paint blue, what I can put on the B site, and then I ignore all the stuff that I don't want to work on because, you know, it's going to kill me in the course of doing the experiments. I have basically 3/4 of the periodic table covered. It's incredibly chemically flexible. There are many, many perovskites, lots of flexibility. That's a good start, right? That you can make many different compounds. I'll also point something out, which I think is not a very widely known fact. Maybe you never heard of perovskite before today. Surprise for you, it's the most common crystal structure on the planet, right? What do I mean by the most common crystal structure on the planet? Most of the mass of our planet is actually perovskite if I ignore what's liquid. If I look at the solid mass of the planet, it's mostly perovskite. And it's mostly perovskite because of this material, magnesium silicon oxygen 3. It's an iron-bearing mineral. This is what the Earth looks like. This is the liquid inner core. This is the lower mantle. 70% of that lower mantle is made up by this magnesium silicon oxygen 3 perovskite. It's a very, very common structure, really important in Earth science, deep in the Earth. There's not a lot of it on the surface of the Earth, which is why there haven't been many experiments done on it until the last 50 years or so. Okay? So, there's a lot of perovskites about. That wouldn't be enough on its own, I think, to get people really hyped up about perovskites. So this is what gets people hyped up about perovskites. Over the years, there have been discovery after discovery after discovery, which has really shocked people, that has happened in perovskite materials, right? So this is what I meant with my earlier comment. If some chemist, some lucky chemist had gone through and looked at all the transition metals, this is the stuff they would have found, but they didn't, right? So in the mid-80s, high temperature superconductivity was discovered in this basic structure. I'm going to talk about that in a second. That was an incredible surprise. These materials can be magnetic. They can exhibit an effect called colossal magnetoresistance that I'll talk about later. They make great dielectrics. They make wonderful semiconductors. And they have a very nifty property that they can conduct not just electrons, but oxygen. So you can make an oxygen separation membrane from these things. You can have a millimeter thick sheet of a perovskite, put air on one side at relatively high pressure. Only the oxygen will come out on the other side of the separation membrane, okay? So let me talk about one of these things in a bit more detail. It's a fascinating story. I could talk about this for an hour, but I won't, which is probably a relief, right? So copper oxides, high temperature superconductivity. Let me go back to the very beginning. So the very beginning of the story with superconductivity starts with this man here. This guy's name's Kamerlingh Onnes. He was in Holland at the time, around about 1900 something. And he had a mission, and he really was a man on a mission. His mission was he wanted to liquefy the last remaining noble gas, right? The last thing in this column that had not yet been liquefied, which was helium, right? Nobody knew what the boiling point of helium was going to be, but they knew it was pretty low. And he was in a race with a couple of other people to do it. And he succeeded first in a really large-scale effort. This was his lab. And he found that it boiled at 4.22 K. He could make it reliably. And he wanted to do some experiments with it. And one of the experiments he did is he measured the electrical resistance of a metal, it was mercury, as a function of temperature. And he did this because the best theoretical physicists of the time had told him one of three things must happen, right? We can't agree on what's going to happen, but we have three scenarios. One is when you cool the lattice down and the lattice stops vibrating, that the resistance will go exactly to zero only at t equals 0. He was never going to get to t equals 0, just approach it. It would asymptotically approach resistance 0. That was one possibility. The other possibility that some people thought, including this guy who's in the picture, maybe somebody knows, you can tell me later who that is, that person said, actually, when you cool you cool this conductor off, what's going to happen is that delocalized sea of electron that you learned about in 3011, those electrons are going to go back to the ions they came from. They're going to freeze out, and the resistance will shoot up to infinity. Okay? And then there was a third possibility. Some realists said, well, I don't think it's going to come down to actually 0. There'll be some defects in any real sample. Those defects will scatter a little bit, so it should come into a constant. Right? So he's looking for one of those three things. And of course, classic scientific discovery. What did he find? None of the above. Right? He found the fourth thing. So he found that the resistance was going to come in, looked actually like, people who thought there would be a constant resistivity were not far off. And then he got to 4.11 Kelvin, and something bizarre happened. The resistance of his mercury fell as close as he could tell to 0. And even back then, close as he could tell was actually pretty good, 10 to the minus 5 ohms, right? We now know that this number really is truly 0. And we also know that this is not the only surprising property of superconductors. They have some other properties too. So this thing is called the superconducting transition temperature, or the critical temperature. And of course, you can imagine, once this very interesting thing had been discovered, he won the Nobel Prize for this, people wanted to find, well, is superconductivity rare? Is it normal? Does it happen a lot? And so this is superconducting transition temperature as a function of time, right? So there's mercury. This is what Inez found in 1911. Very quickly, everybody went through the elements. That was very educational. Superconductivity is not rare at all. It's very common, lots of elements of superconductors. But the TC never went above about 10K, right? And liquid helium's super expensive. So this is sort of a problem. Then people went and they, did a lot of work on alloys. Alloys, you can get up to maybe 20, 25K. And then somewhere about here, another Nobel Prize gets awarded. First group that actually theoretically explains how superconductivity works. And that's when the field sort of died a little bit, because they showed very clearly the TC couldn't really be much more than about 30 or 40K. So don't bother looking for something that's more than 30 or 40K. It isn't going to happen, okay? And that was the status quo. Not a lot happened until 1986. These two people, Bednorz and Muller, stories vary massively on exactly what they were trying to do. Some people said they were really looking for this. I've heard some other crazy things. They were trying to make ceramic humidity sensors. There's absolutely nothing to do with high temperature superconductivity. But they found, in of all things, a perovskite oxide, lanthanum, barium, copper, oxygen, that they could get a TC that was about 30K, right? And this was a real surprise. No oxide superconductivity to speak of at that time. In fact, the person who had discovered the most superconductors ever, a person called Bernd Matthias, wrote down a list of rules to guide people to find superconductors. One of them is hilarious. It says, avoid theorists, right? That's literally in his list of things to avoid. One of them, very explicitly, avoid oxygen, eliminate oxygen. There are no good superconductors that have oxygen in them, right? So, this was a Nobel Prize winning discovery, followed only months later by the discovery of a superconductor, YBCO, yttrium, barium, copper oxide. I'm going to show you it in a second. Ceramic material that has a TC of 93 Kelvin. That's above liquid nitrogen temperature. That's a big deal, right? So people start to think, maybe I can get TC to room temperature. If I can get TC to room temperature, I could pass electrical current around the world with having basically no voltage developed, no loss of electrical power, okay? So at this point, I have a little demonstration which I think some of you have probably seen before, but maybe some of you haven't seen before. I have a piece of YBCO. I am dipping it in liquid nitrogen, trying to get it really thoroughly cooled down. And what we have on the track here is a series of magnets, very strong rare earth magnets. That doesn't work too badly, okay? Those strong rare earth magnets are generating a magnetic field. The magnetic field comes up and out of the track. In addition to having zero resistance at this temperature, this thing also expels all magnetic fields. It turns out having zero resistance and expelling all magnetic fields go hand in hand together. So it levitates on top of the magnet, right? It's repelling the flux that comes out of the magnet to the point that it can levitate. And if you put it on a track like this, it will do all sorts of cool things, like completely spin, levitating around the track, which of course makes you think, why don't I build a train that works on this concept, right? And in fact, that's already been done. It's a super expensive train because you got to cool the track to a very low temperature. And of course, what we hope we'll be able to do one day is, if we understand how this works, that we might be able to get that temperature all the way up to room temperature, so you can do this kind of thing without any coolant, or with much less coolant, okay? So that's interesting, okay? Let me tell you the bad news about that, right? There have been 100,000 scientific publications written on the topic of cuprate superconductors since 1986, and there is no agreement on exactly how that violates the theory of superconductivity that was worked out in the 50s, okay? So that's a bit of a bummer. There's a huge amount of effort gone into it, and it's not really very well understood, okay? So you could imagine this happens in the 80s. Nobody's paid any attention to perovskite oxides. You can imagine what happens next. Every conceivable perovskite oxide is made very, very quickly. And it was just a few years, about 5 years, that another really fantastic effect was found. It's called colossal magnetoresistance. How to get the name colossal magnetoresistance? First of all, it is actually colossal, so it's a good name. And second of all, the name giant magnetoresistance was already taken, so, you know, they had to think of something, and it was colossal magnetoresistance, like right? Olives. Olives?
Yeah, that's how you name olives.
Okay, I don't see the connection. We should talk about that afterwards. Okay. So this is it's a manganese oxide, what's called a manganite. It has this terrific property that this is electrical resistance as a function of temperature. It looks like it's going to be an insulating material, goes magnetic, becomes a magnetic material, and decides it wants to be a metal instead. And then as a consequence, when you apply a magnetic field, you get a colossal decrease in the resistance. To give you an idea, the giant magnetoresistance that got everybody so excited, that actually fueled hard disk drives for 20 years, that was about 10%. Right? And this is literally thousands of percent in a couple of Tesla magnetic field. The record is in fact 10 to the power 12. It's a ginormous number, right? Colossal is a really good name for it. Okay? So let me tell you a history lesson about this. I know Frank likes this slide very much. This is citations per year as a function of time for 5 papers, right? I want to illustrate the weird way that science works. These manganites were first made about 1953. And in 1953, everything was there to discover colossal magnetoresistance, and they just missed it. They had pretty bad ceramic samples, and they didn't conduct electricity very well. They didn't apply a very big magnetic field, and they missed this thing. It was sat literally in people's drawers for 2 decades. They didn't do anything about it. Good samples came along in the early 90s, and these 5 papers were understood to be extremely important, and then all of a sudden, people start citing them, right? So they're, you know, classic papers where we didn't really know how good they were until sort of 40 years after they were written, right? So this kind of thing cannot happen to people like Professor Bates and Zasadinsky and Professor Frisbee, but for me, this is inspirational, right? Because if I publish some papers that nobody seems to care about, I can convince myself that in 40 years they're actually going to be classics, right? So unfortunately, I'll probably be dead at that point, so it's not so good, okay? So perovskite oxides, all of that wonderful science, what do we use them for? Well, we use them for a bunch of stuff, but I really hope that there's a bunch more to come, right? So they've been used in capacitors since the 70s. They're used in catalysis a lot. They're in a commercialized technology called ferroelectric RAM. First thing that had a ferroelectric RAM in it was a PlayStation that Sony made. It's now used in a bunch of niche applications. It's a non-volatile RAM, so you use it where battery failure is a possibility. It's used in slot machines. It's used in ATMs, things like that. And then solid oxide fuel cells. So this is a really incredible technology. You burn a hydrogen-containing gas in the presence of oxygen. If you have a perovskite that can conduct the oxygen, you can generate electricity, so it's a battery. And the only waste product is water, right? Which is fantastic, right? Imagine you can burn something without having carbon monoxide or carbon dioxide as the waste product and generate electricity. That's really fantastic, okay? And then this is the one that I will talk about for the rest of my time, oxide electronics. The idea that we might be able to do something with perovskite oxides that's better than silicon, okay? So to motivate that, I want to show you this picture. And a quote, a very famous quote by Herb Kromer, who won the Nobel Prize in 2000 for semiconductor heterostructures that look like this. He said, "The interface is the device." And what did he mean by that? He meant there is no modern microelectronic device that doesn't work by virtue of its interfaces. They all work by virtue of their interfaces, right? And a classic example is a transistor. This is what the transistor looked like, Bardeen, Brattain, and Shockley. They won the Nobel Prize for it in 1956. 3-terminal device looks like that. This is what it looks like in 2015. It's exactly the same thing. It's just scaled down by a factor of 1,000,000, right? And 1,000,000 is a really big number. And the way this device works, it works the way it works because I have an interface between silicon and an oxide and a metal. If it didn't have the interfaces, it would have no such functionality, okay? And I mentioned to you earlier, just going from SiO2 in this layer to hafnium O2 costs more than $1 billion of research money, right? And the reason it's so difficult, if you think about that, if you want materials with very different properties, you've got to look for materials that typically have very different structures. if they have very different structures, it's hard to put them on top of other materials and get them to interface well and have low defect density. And that was what was so difficult about that problem. So what the complex oxide people ask is there a way that we could use complex oxides that would get completely around this problem? And the idea is really, really simple. If I have all of that functionality that I just spoke about in one single structure, I don't have to find materials with very different properties, very different structure to get very different properties. I can use the exact same structure, change a couple of the ions, and get whatever functionality I want. If I want a magnet, there's one in the perovskites. If I want a semiconductor, I have one. If I want a metal, if I want a ferroelectric, everything I want, and I can layer them one atop the other with the same lattice parameter, same crystal structure, good thermodynamic matching across the interface, right? It's a very compelling idea. There are obviously problems, right? There are things that we still have to work out, but that's the basic idea. People draw pictures like this all the time just to give the impression anything I can dream up, I could build this stack of materials, and it should be much easier than it is with conventional materials, right? So you know there's got to be some problems. I'm going to talk about one of the problems, but this is the basic selling point, okay? And this is the last piece of introduction, right? And I'll have 5-10 minutes worth of data. You might wonder to yourself, okay, so it cost $1 billion to get to hafnium dioxide, but still works great. Right? So why do I care, right? What's wrong with current microelectronic devices, okay? Well, if this slide doesn't disturb you a little bit, right, then I haven't done a very good job of explaining to you what's in this slide. This slide should really shake you up a little bit, right? Because you need computers to keep getting better, because you're using them in more and more complicated ways. You need more processing power and you need more data storage, okay? And this shows, you know, the famous Moore's law, right? Transistors just keep getting, you know, more and more dense as a function of time. That's fantastic. You hear all this gloom and doom about Moore's law, and it's a really important thing to worry about, right? Because, you know, they're talking about 14, then 10, then 7 nanometer devices to keep that Moore's law going. And a lot of people think that just flat out isn't going to be possible. But it's always sort of future tense, right? So there's a sort of, you can imagine, well, it's never going to happen. People just say it's impending doom, right? But look at this green curve. It's not impending anymore. It's actually past tense, right? The end of silicon has already started, right? So this green curve is the clock speed at which Intel and other manufacturers are running the chips that they make. It's flat. In fact, it's going to go down. It's almost guaranteed to go down. They can't run the clock any faster at these sizes because it gets so hot that you literally degrade the device and eventually you would completely melt the chip, okay? So silicon running out of steam has happened. We know it. It's on a graph. This thing is going to flatten out at some point. And this is a totally different ballgame than it was. You know, when I was a grad student, I remember very clearly, I figured out very early on, you never say anything bad about silicon because everybody just gangs up on you, right? You never say I might have a material that could compete in any way with silicon because it's ridiculous. That whole tone of that conversation has completely changed. If you spend any time around people who really understand this industry, you read what they write, you realize they're desperate. It's a whole different ballgame now. They are desperate for people like us doing basic scientific research that could eventually replace what they're doing with silicon because they know that the game is almost coming to an end and they're really looking for other ideas, right? And I'm not saying it's necessarily going to be perovskite oxides, but you know, you have to bet on something, right? So I said, you know, what are the problems? So let me show you one. It should only take 5-10 minutes of a problem that we've attacked in the field of complex oxides that I think we have a reasonable solution to. We've definitely made some progress. So this is kind of a technical slide. I'm going to explain it in very, very simple terms. This problem is called the dead layer problem. And this, you know, didn't appear at first. It took a while before we realized we start putting these interfaces together. There were some really promising things early on. I will show you that the structures look amazing. They look so beautiful, they look so perfect. It's like, wow, what people said is going to work might actually work. And then you start measuring the properties and you realize sometimes even though the structure looks fantastic, the properties are lousy, right? And in, you know, one specific thing here, so we took a specific kind of material, so magnetic material, manganite, in our case it's a cobaltite. It's supposed to be magnetic and it's supposed to be metallic. And it turns out when you make it very thin, when you're very close to the substrate, to the interface with the other perovskite, its magnetic properties get worse and worse and worse, and eventually they completely disappear. And its conductivity gets worse and worse and worse, and eventually it completely disappears. And the whole field started to realize that when you get down to thicknesses of about 10 unit cells, you definitely want to make devices thinner than that. When you get to about 10 unit cells, the properties you expect it to have are unrecognizable compared to what you actually have in a very thin film, okay? So that's a serious problem, and we wanted to know, is this a fundamental limitation? Does this scupper everything that I just explained to you about the potential of perovskites, or, you know, is there something that we can do about it? So this is how we make this stuff. If you're ever down in my lab, and you're welcome to come and have a look, you'll see these big chunks of stainless steel. They're used to do things like sputtering and molecular beam epitaxy. This is one of those processes running. This is a perovskite substrate. It's been heated up to 900 degrees C. These things crystallize at pretty high temperatures, and we're literally raining down atoms from a plasma in a sputtering process on the surface of that thing. And if we get all of the conditions exactly right, then we will grow the perovskite structure that we want, the A1, B1, oxygen 3, and we can do some experiments, right? So how do we know if it's right or not? Well, there's a bunch of ways to do it, but this is one that for us has just been tremendously useful. Bit of a mouthful. Scanning transmission electron microscopy with electron energy loss spectroscopy. Everybody just calls it STEMILS, right? For obvious reasons. Okay, we have one of these machines. They're very expensive, powerful machines. This is a $4 million microscope that sits over in Shepherd Lab in the characterization facility. It says Titan on the side. I'm always sort of surprised that it doesn't say Andre McCoyan's baby on the side, because that's basically, you know, what it is, but he hasn't gone on there and painted anything on the machine, it turns out. And what does it do? It basically makes a very, very tiny beam of electrons. The beam of electrons is less than an angstrom wide, right? Think about that. That's ridiculous, right? A hydrogen atom is 0.53 angstrom Bohr radius. This goes down to less than the width of 2 hydrogen atoms. It fires it into a thin part of your sample. You measure the electrons that come out at really wide angles, and you scan the beam around and you make a picture. And then while you're at it, the electrons that fly through the middle, you put them into a spectrometer and you identify chemically what they went through. So you can pick out single atomic columns, and you can also know exactly what chemistry is involved in that particular column. And this is, you know, it's a game-changing thing in material science. So this is a picture. Lanthanum strontium cobaltite, one of my favorite magnetic materials. It's grown on top of a big slab of strontium titanate. You're looking at it from the side. This is just vacuum. This is the film, and this is the interface with the substrate, and this just shows it getting to higher and higher magnification. The magnification here is a little bit over 1 million times magnification, and this is the interface, and you look at this thing and you think, wow, this is just fantastic. It's exactly what I drew. Literally cubic perovskite growing on top of cubic perovskite. I don't see any defects anyway in the structure. This looks just fantastic. And then you go away to your lab, you do a simple electrical resistance measurement that costs maybe 10, 20 bucks, and you realize this stuff is awful, right? It's really bad. It has lousy magnetic and electronic properties, right? So why? So this was pretty cool for us, right? So this is not just looking with electron microscopy. The structure was perfect practically every time. We're looking here with the spectroscopy part, and we're mapping the holes. If you remember from MATS I-3011, if you've done 3011, you grab an electron from the valence band, put it up to the conduction band, you leave this mysterious thing behind, which is like a positive charge that moves around, right? That's a hole. Our material happens to be a hole conductor, and we had a way spectroscopically to map those density of holes as a function of position. And this is, you know, you look at the structural map, it's perfect, and then the electron microscopist shows you this, and you're like, oh my gosh. I mean, it just looks awful. It's heterogeneous, it's lumpy, and in particular, this part got us really interested and excited. There's a clear depletion of the charge carriers at the bottom of the film. That's obviously why this thing has a dead layer of about 10 nanometers thick. Doesn't have any holes left at the bottom of it. Why doesn't it have any holes left? Well, we also mapped the oxygen, and it turns out there's about 2% less oxygen on the bottom. So somehow we like to make oxygen defects called vacancies, literally missing oxygens, and those oxygens like to pile up on the bottom, okay? Why does that happen? Well, this was the key image in this piece of work that we did. Instead of working with these thick films, we decided, well, why don't we grow a very thin one, just the size of this dead layer. Here it's 7 nanometers thick. Let's image that and see if it still looks quite so perfect. And you can see with just the naked eye, it doesn't look quite so perfect. You see these dark stripes, right, that run perpendicular to the interface in this material. What are these dark stripes, right? So we amplify this image. This is really sort of amazing. You can go in, pick out the atomic columns. This is the cobalt oxygen column. This is the lanthanum strontium oxygen column. And you realize this is all about the cobalt oxygen column. The cobalt oxygen column basically goes dark, bright, dark, bright, dark, bright, dark, bright in exact alternation. Okay? And it did not take us very long to figure out what was going on here, because we put the electron beam on the dark stripe, we measured the oxygen content, much less than 3, and then we put it on the bright stripe, and it's exactly 3. So we discovered something really pretty amazing. The oxygen vacancies, you tend to think of those things as being random. In this material, they're not random. They line up into stripes, and those stripes run in a very specific direction, right? And the question, of course, was, why do they do this thing? It's oxygen vacancy ordering. We can find some obscure compounds where oxygen vacancy ordering happens, but it shouldn't happen in this material, and we found it was there, and it's only there at the interface, right? And I can tell you, this was very exciting for me. I was on an airplane. I did not have my computer. I had a big piece of paper with this printed out, and I had a ruler and a pencil. And I was doing all sorts of stuff with interplanar spacing. I was actually looking around for something else. And of course, we knew if you take the oxygen out of one of the layers that its lattice parameter has to go up a little bit. The oxygen is the glue, and the one next to it has a little bit of a smaller lattice parameter. So we knew this thing was modulated, but I hadn't understood the significance until I took the average of these two numbers. The average of those two numbers is 3.93 angstroms, and the lattice parameter of the substrate is 3.91 angstrom. And it was like, wow, that's fantastic. I kind of get this now. I get this because what the material has done is really smart, right? The way it normally makes up its mismatch with the substrate is you put in dislocations at a massive energy cost. This thing figured out, okay, if I can form oxygen vacancies at a much smaller energy cost and I can line them up into stripes so that I can expand my in-plane lattice parameter, I can exactly match the substrate, right? And it solved a problem for us, which is had really disturbed the microscopists we were working with. We never found any dislocations, right? And then we understood, why do we not have any dislocations? Didn't need any dislocations. The material was lattice matched to the substrate in a completely new way. So that was pretty exciting. And then we had a few months where we had a lot of fun with this, because once we'd seen that perpendicular image, we realized if I just mess with the substrate, I can control this. I should predict exactly what's going to happen. I know the vacancies like to run along the 001 direction. I just changed the orientation of the strontium titanate 110. We predicted they should run at 45-degree angles. They do. And then this one, nail in the coffin, right? We also said, well, let's flip the substrate. So instead of putting the material under tension, making it expand this way, let's compress it this way. It should have to expand out of the plane, and I should put in parallel sheets of oxygen vacancies that run parallel to the interface. And that's exactly what happened. And we knew that we had this sort of figured out, okay? So you can control how many oxygen vacancies you have, what direction they run in, exactly how they order, just by basically flipping around the substrate on the bottom, okay? So this is really technical, but I just want to show you what happened when we did this. So this is what I showed you already, the STO-001 with these perpendicular stripes. This is the oxygen crashing down. This is the holes crashing down. You go to these other substrates. This is what everybody had been using, and the oxygen content as a function of position just becomes absolutely ramrod flat. It also gets smaller and smaller as you go to these compressive strains. This is what happens to the dead layer thickness. 19 unit cells, 11 unit cells. I'll show you our guess. Best is it's less than 3 or 3.5 unit cells if you properly choose the substrate so you can manage these oxygen vacancies. So this is the kind of thing that is as good as we can do. It's about 6-7 unit cells thick. It's a metal, resistivity versus temperature. Just looks like it is in the bulk. And if there's a dead layer on this thing, if the dead layer at the top is the same as the dead layer at the bottom, then 6 divided by 2, about 3 unit cells is the thickest that dead layer can be. We've come a long way since growing them on the 001 surface where it was 20, and some people were getting even bigger numbers, right? So I'm going to wrap up. I spoke 4 minutes too long. This is my summary. If you take away only one thing, take away the top bullet, right? I think it's a fantastic time to be doing materials research in this area because of that situation I mentioned with microelectronics, right? There's an industry that's desperate for people to come up with better alternatives. And there's a whole bunch of crazy things that people are trying to do. And I think it's just a fantastic time to be involved in basic research in that kind of area. Something has to happen, right? A revolution has to happen. Something's going to work, okay? So complex oxides are just one potential way to get around this problem. The really pressing problem at the moment is heat, right? That's what's making that clock speed go flat. On oxides, you know, one way to do it. There's a lot of complicated things people have thought of that they might be able to do with oxides I didn't talk about. Of course there are problems, but we're making rapid progress. And, you know, I showed you an example where it's a sort of a familiar story. Defects aren't always bad, right? So acknowledge the people who did the work. A few of them are here, right? So there's people from my group. People who've been involved in this. Jeff Walter, grad student, who's right here, who's doing the stuff that's come after what I've shown you here. doing other things with those ferromagnetic materials. And then this picture, I want to emphasize one thing about this picture. Undergraduate student, Lindsay sat right there. Okay, where else do we have undergraduate? Undergraduate student, undergraduate student, undergraduate student, undergraduate student, undergraduate student, undergraduate student. So, you know, please take this opportunity to do undergrad research if you haven't taken it already. It could be a really fantastic experience, okay? So with that, I'll take any questions and thank you for your attention.